All right, it's semester 1, 2021, and I'm doing a second revision seminar for Maths 1A, and today we're talking about integration. Welcome to everyone online and everyone face-to-face, and hello to those of you watching from the future. Yes, we can do as much deaf applause as we want. Okay, so as I said just before I started the recording, integration is a really big part of this course, and it has quite a few interesting techniques. And so I'm going to talk about the techniques for finding integrals, and then if there is time I will talk about a couple of the theorems and upper and lower sums, but we'll see how we go. Okay, so once upon a time, Newton and Leibniz invented calculus, and they discovered that integration and differentiation were connected to each other. Integration was designed for accumulating things. You can do a running total of how much stuff has been accumulated so far, and that's what an integral is for. And differentiation was finding about the rate of change of things, and it turns out they're related. And it turns out that when you do the integral of a function from one place to another, then it comes out to be this, which is short for this. As long as the derivative of this capital F function is the little f function. That's the, I believe, second fundamental theorem of calculus. So the second fundamental theorem of calculus says how to do an integral. So it's saying that when you do a running total of the function f of x from a to b, taking into account how much time it spends being each function value, then it's the same as finding an antiderivative and just subtracting that between the two ends. And just for completeness' sake, the other fundamental theorem of calculus is the other way around. It says that if you create a function as the running total of another function, so this is the running total of f of t starting at a and going up to x, then when you do the derivative of it, you get the function you first thought of, but in terms of x instead of t. These are the two fundamental theorems of calculus. This theorem is the one that tells you how to do an integral. This theorem tells you that antiderivatives actually exist. So basically it's saying if you want to create a function that does differentiate to produce the function you were thinking of, integrate it. And if you want to find the answer for your integral, think of a function that differentiates to give the function you were thinking of. It seems like circular reasoning. There you go. They're just so deeply connected that there's nothing that you can do about it. But that's why there's two theorems. One is how to find an antiderivative using integrals. The other one is how to find an integral using antiderivatives. That's the difference between them. So I think this one's the first one. Is that right? But I remember this one better because this is how to do integrals. Okay. Someone has, I've forgotten your name, but someone has asked an intuitive understanding of that. I'll see if I can do that before I do the actual integration bit. Be back in just a moment. I'm not leaving the room, but for those who are in the Zoom. No. Here's an x-axis, here's a y-axis, and here is a function. Oh, that'll do. All right. So if I want to create a function which is the running total of these values so far, then that function, I'm just going to draw. Anyway, I'm not going to draw. The running total of this function so far, then the running total would look like this. It would be that at this point, and it would be both of these at this point, and it would be all of these at this point, and then it would be all of this at this point, and they would just keep stacking up higher and higher and higher as you went along. And that would be the running total of this function, like that. And that running total would always be getting higher no matter where you were. But it would be getting higher slower in places where the function value is lower, and getting higher faster in places where the function value is higher. So the speed at which the running total increases is the current height of this function. That is what this says. This function is the running total of this function, and the speed at which this changes is the height of the function at the moment. That's my intuitive understanding of it. How do you feel about that? That's pretty much it. It's all about making running totals. Yeah. These are Cuisenaire rods, if you ever wonder what these are called. A big box of them in the Maths Learning Centre if you ever want to play with them. Okay. So that's the intuitive understanding of it. And the difficult bit, if you want to find a definite integral, because really definite integrals are what integrals are for, is to imagine how do you think of something that differentiates to give the thing that you've got. And that's what all these techniques of integration are for, and I'm going to talk about them now. Okay. All right. In this course, you have been taught 4 techniques that have names, and a couple of others that they weren't named. And I list them in this order. So these are the techniques of integration in order of hardness. Technique 0 is just do it. It's called technique 0 because it's not really a technique. You just happen to already know what the antiderivative is. Okay? In this category is knowing your derivatives. For example, you know that the derivative of sine is cos, and so therefore the integral of cos is sine. Okay? And things like when you've got a power, put the power up by 1 and divide by the new power. Put the exponent up by 1 and divide by the new exponent. That sort of thing. E.g., x to the 5 goes to put the exponent up by 1 and divide by the new one, for example. And for example, the integral of 1 over x dx is ln of the absolute value of x plus c. I didn't mention the plus c thing. The plus c thing is about the fact that this, if you can think of any function that differentiates to give your function, then adding a constant to it won't change what its derivative is. And so this symbol here is to say what's all of the antiderivatives. Someone's asked, are we covering the upper and lower sums thing today? My plan was to do that, yes, but it's going to probably be at least an hour from now. All right.
Could you explain plus c visually?
The main thing that helps me explain plus c visually is two things. Just give me a moment. Whoa. Right, so here's a function, and I'm going to create a new function, which is the integral of this function from a to x. All right. This function, this blue function, is the running total of this red function starting from the position 1. So here we are at 1. There. Okay. So when I move this forwards, no, oh crap. No, I don't want to do that. Okay. When I move this point forwards, oh, come on. Yeah, it's good enough. You look at David making Desmos activities on the fly. Okay, so here we are at x equals 1. And I can do the running total of the area so far. And so as I move forward, as I move this point forward, the area gets lower and lower because I keep adding negative and negative bits. And then at this point, it starts getting higher and higher again. But if I had started it at a different spot, started my running total area later, then the values would be different heights. It's a little easier for me to draw this on a on the thingy. Let me go back to here. So here's a function. If I start my running total area here, then that function will be 0 at that spot, and then it will keep going up. It won't go up quite so fast here because it's not going up at all at that spot. And then there's more and more area here, and it'll just keep going up and up and up like that. So that's this function here. It starts at this, the running total of this spot. This is f of x is the integral from 1 to x of f of t dt. But what if I had started it over here instead? Then the area would have been bigger by the time I got to this spot. It would have started with no area so far, and there'd be more and more area, and then the area would keep going up, and then it would stop, and then it would keep going up again. And this would be the function starting at 0. And this function is the same as this function, but it's higher up. And it's higher up by the amount of extra area I had by starting at an earlier spot. How do you feel about that? Yeah. So that's one of the reasons. And the other reason is that functions that are higher up or lower up have the same slope at the same places at the same x value. If I've got a function like this and a function like this, at this value of x, the slopes are the same, even though the functions are different. That's the plus c here, that difference there. But it doesn't make a difference to the derivative. Yeah. Okay. Back to my techniques. So, just do it. Know your derivatives. The other one, I'm going to put one here in a minute, but I'm going to fill it in later, if that's okay. Technique number 1 is rewrite it a different way. For example, maybe you'll expand it out. Or maybe you'll factorize it. Or maybe you'll use some sort of trig identity. These are all ways of rewriting things into a format that's easier to do. I'll show you these techniques in a minute. I just want to list them all. Okay. Technique 2 is substitution, which is specifically designed for when there's a function inside a function, or when one part of your thing that you're integrating, it looks like the derivative of another part. So when one part's almost a derivative of another one, substitution will be helpful. It's sometimes also helpful just when there's stuff inside other stuff. But this is the main time when it's helpful. So that's what it's for. Technique 3 is integration by parts, which is designed for when you have two functions multiplied together and you know how to integrate one of them. I'm just going to put that on a new page. I just will point out that sometimes the two functions that are multiplied, one of them is the number 1 and you have to put it in yourself. So, and the number 1. And sometimes, no, that's pretty much what it's for. But I wouldn't try to do by parts until after you've done substitution. Tried substitution. Yep. So is this a one function and the number 1. And technique 4 is trig substitution. Which is a fancy kind of substitution. So you could put it back at this level, but I'm putting it here because I wouldn't try it. And trig substitution is specifically designed for getting rid of annoying square roots. Annoying powers of, well, yeah, mainly square roots. For things with Pythagoras bits. So, you know, square roots of that sort of thing. The sort of thing that would happen if you did Pythagoras' theorem on something and you got a square root with something squared plus or minus something else squared. That's the sort of thing that we're going for. Yeah. It's specifically designed to get rid of annoying square roots. And technique 5 is partial fractions. Now, partial fractions is not technically a technique of integration. It's a way of rewriting things. So this is a special of technique 1. And this is a special of technique 2. If you do a later maths course that probably differential equations 2, then you will use partial fractions for other purposes that aren't integrals. There are integrals nearby, but you know, that's a whole other thing. And this is for rational functions, which are polynomials divided by polynomials. Okay, these are the techniques. I'm very clever. No, can't fit them all on one page. Okay. So, how do people feel about these techniques? Which one is the one that you feel most uncomfortable about? By parts? Everyone has a different one. Substitution? Trig substitution? Some people have a particular substitution that they don't like, situation. Everyone has one that they feel grumpy about, and that is your right, and you should own that feeling. And what we're going to do, what some people said, I've missed a whole lot of chats. Trig sub, yeah. That's the one. Okay. Hayden's asked, are there any conventions for which is the best trig sub to do? I will cover that. Okay. The hardest part of integration, as hard as trig substitution is, the hardest part is deciding which one to do. And one reason I have this list is that you can run through the options. I'm finding that distracting. You can run through the options and decide which of them, and knowing that these earlier ones are easier than the later ones. I mean, technically trig substitution is the actual hardest. I should probably put that last, but knowing that these earlier ones are easier than the later ones, you can try the earlier ones first. Or you can imagine what would have happened if you did try them. Okay. Under the just do it, there is one more category, which is I call divide by the constant derivative. It's technically a kind of substitution, but it happens so often you're allowed to do it without saying that you did substitution. And the example goes, I would know what to do if that was just an x. I would put the power up by 1 and divide by the new one. But it's not an x. It's a 3x plus 1. And the derivative of 3x plus 1 is a constant. So I'm going to have to divide by that constant. It's like the chain rule, but backwards. But it only applies when the derivative of the inside is a constant. I will keep using that over and over. You will see it as we go. But I put that under the just do it category. It is so common that you need to be able to just do it. Okay. Right. So what I'm going to do is I'm going to find some integrals. And if anyone has integrals that they have found difficult, please tell me them at any point. Okay. And I'm going to do some examples. All right, here we go. I have x times 3 plus 5x squared. And the 3 plus 5x is all squared, but the x isn't part of the square. How would I do this integral? So I'd run through my list. Can I just do it? Well, if the x wasn't there, then I could, because the derivative of this thing is 5. So I could have put the power up by 1 and divide by the new power and also divide by the 5, and that would have been okay. But the x is there, and so that's a problem. The next thing on my list is to rewrite it. I reckon I could expand it out. So 3 squared plus 2 times 3 times 5 is 30 plus 5x squared, 9x plus 30x squared plus 25x cubed. And now I can just do it. all of the techniques are designed to turn it into something that you can just do. So the 9 will still be there, and the x is currently to the power of 1, and so I will put that up and divide by the new power. The 30 is still there. That will go up to 3. I'll divide by the new power. The 25 is multiplied on, so it's still there. This will go up to 4. I'll divide by the new power, and I'll whack a plus C on because that's the rules. And ta-da. So that's one way I could do it. Expanding out is not usually a bad plan. Unless the thing's on the denominator. Never expand out a denominator. Or not never, but almost never. It's not a good idea to expand out a denominator. You would never encounter this function in life, but we're getting good at this, okay? So we're going to try different options. This one is extremely similar to the one I just had. It just has an extremely large power. It is not impossible to expand this out. Wouldn't recommend it. So I still can't just do it. If it was this, I could just do that. Power up by 1, divide by the new exponent up by 1, divide by the new exponent, divide by the derivative of the inside. That's great because the inside's got a square, got constant derivative. Could just do that. But I can't because of the x. So the next thing on the list, so I could attempt to factorize it. I mean, it's already mostly factorized, so that's not helpful. Trig identity doesn't have any trig in it, so not going to be rewriting that, probably. But I could do substitution. Substitution is when one part's almost the derivative of another part. X is so not the derivative of this, but I'm going to show you substitution will still help. Watch closely. Substitution is also designed for when one part is just another function inside another function. So I'm just going to hope that this helps. Yep. You can do that by parts. And we'll do that too. Okay. So, so this bit. So now I'm going to talk about how substitution works. The point of substitution is to remark your x-axis in terms of a different function. And what that's going to require you to do is to change the function itself, but also this dx is about how, when you move along the x-axis, you're moving at a constant speed, it's about how much time you spend being each function value. And so if you've remarked the x-axis in terms of different numbers, then you'll be spending more or less time at certain function values. So that's why you change it. Yeah, it's about the speed at which you're moving through the function values, and you've got to take that into account. So if u is equal to 3 plus 5x, as x moves forwards, this moves forward 5 times faster. And so I've got to take that into account when I do the running total. All right, so the first thing to do when you've chosen what your thing that you're going to replace with u is, and you don't have to choose u, you can use another letter if you like. Over in the USA, they call this u substitution. It's just substitution, people. You don't have to use u. Okay. Just moving on. So the first thing to do is deal with the dx. So I'll figure out how quickly u changes when x does, and it's just 5. And then I'll figure out how to replace the dx with something involving du. This is how I do it anyway. So I'm going to divide both sides by 5 and multiply both sides by dx. And this is saying that a tiny change in x corresponds to a fifth of a tiny change in u. And so now this dx here can be replaced with 1/5 of du. Okay. And this 3 plus 5x is going to be replaced with a u. And then what I have left is an x, which also needs to be replaced with something in terms of u. So what I'm going to do is I'm going to go back to the beginning. and I'm going to rearrange this to figure out what x is in terms of u. Like that. And now every part of this can be replaced with 1/5 of u minus 3. This can be replaced with u, and this can be replaced with 1/5 of du. And every piece involving x can be replaced with a piece involving u. Okay, so the x is really 1/5 of u minus 3. This is really u, and the dx is 1/5 of du. And now I have turned it into a different integral. This integral, though, that I can expand. So I can use technique 0, technique 1. I've got 1/25 of u times u to the 215. So that's 1/25 of u to the 216 minus 3u to the 215. So those became a 1/25. The u times u to the 215 became the u to the 216. The 3 times the u to the 215 becomes 3u to the 215. And that is an integral I can do. The 125 is multiplied on, so it will still be there afterwards. The u to the power of 216 will become u to the power of 217 divided by 217. The 3 is multiplied on, so it will still be there afterwards. And this will become 216 like that, with a nice big plus c on the end. And I do not choose to expand this out afterwards, but I will replace the u's with what they really are. Ta-da! That was substitution. So, I think someone should ask a question or point something out at this time about what just happened. To help you, the point of this is to know what to do when you're doing this on your own. So is there a move that I did that you could reuse? Yep. So that's, well, there's a lot there. Just a second. Let me see if I can process that. It was good stuff, though. So this bit where you rearranged this so that you could sub this straight in. Yep. And then doing the same thing with the straight up axis. Cool. Other people may have other things, but I like that one. Okay. Now, your classic substitution will look a little differently to that, but I'm going to do this by parts as well, because you said it was possible. What did I start with? 215? Okay. Integration by parts is another thing that you could choose to do when there's two things multiplied by each other. That move that I did in substitution won't work all the time. It tends to only work in that situation where it's thing inside that's linear and thing outside that's also linear. By parts, we'll do it too. Integration by parts is designed for two things multiplied by each other. And what you're going to do is you're going to end up integrating one and differentiating the other. So on a separate piece of paper, I'm just going to write how integration by parts works. It starts with two functions that are multiplied by each other. Some lecturers write them as u and v. Some lecturers write them as f and g. Nobody cares. You can use whatever letters you want. What does your lecturer do? Let's call them u and v. And there will be a u and a v here as well, and there will be a u and a v here as well. So it turns an integral into something that's not an integral minus an integral that you still have to do. So substitution turns an integral you've got into another integral that you still have to do. Integration by parts also produces an integral that you still have to do. I haven't finished yet, because what you have to do is imagine that one of these is already the derivative of something. And the other one is differentiated at the other end. It could just as easily have been this. With this one with a dash here and the other one with a dash here. Doesn't matter, as long as it's a different one on this side than it is on this side that has the dash. I don't remember things in a left to right order very well. And so when people ask me, you know, which one's you, David? I'm going, the first one's always you. And what they mean is which one is going to get integrated and which one's going to get differentiated. And so I will just put the dash where it goes. It took me years to learn how to remember this formula. I used to have to derive it from the product rule every time. But now I know there's a UV in 3 places and there's a dash here and the other one's dashed here. And that helps me remember it. Okay, so if I'm going to use this rule, I'm going to call this U and V. And I'm going to decide which one's got the dash and which one doesn't. And that decision has several pieces to it. Because here we are, we're at a decision that makes integration by parts hard because you have to make a decision at this point. So, 2 things. One of these has to get integrated along the way. The one that I choose to integrate has to be something I know how to integrate. If I don't know how to integrate it, I can't integrate it. I know that, yeah, can't be. If I don't know how to do it, then I can't choose that to be the one that I know how to do. That's the first thing. The second thing is that it has to, the one that gets differentiated has to get simpler. It has to make the whole thing easier to do after it's differentiated. And the third rule is if the other 2 rules don't help, then just choose whichever one you want, basically. So I don't know how to integrate this. I mean, I do, I suppose. Okay, so that's a problem. I know how to integrate both of these, so that's not an issue. I do know that if I differentiate this one, it will become the number 1, and 1 times something, I can deal with that because it's just a number. So that's the one I'm going to differentiate. So I'm going to integrate the other one, and it's going to become this. So that by the time this ends up over here, it will become 1. Okay, cool bananas. So, some people, it helps them to write down the U and the V somewhere on their page. My U was X, and it's going to become a U dash, which is 1. My V dashed was 3 plus 5x to the 215, and it's going to have to be integrated, and so that will be, oh crap, I haven't given myself enough space. So the power, it will go up by 1, 216, I'll divide by the new one, and I'll also have to times by a 5th because of the divide by the constant derivative rule. And so this is now going to be, the U is still X, the V is already a V dashed, and so that's now 1/5 times 1 over 216, 3 plus 5x to the 216, minus the integral of U dash, which is 1, and V, which is 1/5 times 1 over 216, 3 plus 5x to the 216 dx. And I still have to do that integral. I can't be bothered figuring out what 5 times 216 is. If anyone's already done it, feel free to tell me. Sorry? Oh, nice. All right, just I wouldn't normally write this on the page like this. I would just do it, but I just wanted to not have to worry about where this page is going. Okay, so now I still have to do this other integral. The 1080 will still be there because it's multiplied on. I'll have to put the power up by 1, divide by the new one, and also divide by the 5. Sorry, clicked something there. Which is whatever it is. That's a horrifyingly large number. I don't like it. Great. Plus C. And this is apparently the same answer as the other one. So interestingly, the other answer was this, which is actually extremely different to this, but they are the same except possibly different by a constant. Because this one, when I expand it out, it'll have a 3 to the power of 217 in it somewhere. And that constant might be off by a little bit. These are two alternative ways of doing the same problem. Now, I've made it really hard for myself by giving myself giant numbers, but they wouldn't do that to you, I hope. Which one of those do people feel was easier? By parts? That's your call. Whichever one you think is easier, do that one. All right. I will show you one trick with the by parts. This function, oh, let me change it. I'm going to make it harder. No, no, I'm not. No, no. I'm going to go back to where I was. Okay. This integral can be done in multiple different ways. I'd like you to show you all three because I think it's cool, but also to show you that it doesn't matter. You can choose whichever way you want. So if I was going to go through my list, the first thing on the list would be, do I know how to do it already? And the second thing on the list would be substitution, and the third thing on the list, sorry, I did rewriting, and then substitution, and then by parts. And I can do this by all three ways. So I'm going to do all three. So I'm going to do it by rewriting it. I know that there's a trig identity that involves cos x and sin x. It goes like this. Sine of 2x is 2 lots of cos x times sin x. And so that means that cos x times sin x is half of sine 2x. And I know how to integrate that. The half will still be there multiplied on because it's multiplied on at the moment. Sine would differentiate to give plus cos, so it must integrate to give minus cos. Only it's not a 2x, it's not an x, it's a 2x, so I'll have to divide by that 2 as well. Fabulous. I can also do this by substitution. Substitution is designed for when one part of the function is the derivative of another part, and cos is the derivative of sine. And so I see a derivative somewhere, and so therefore I can try to do substitution. Let u be sine x, then du on dx would be cos x, and so du would be cos x dx, and so this bit is du, and this bit here is u. And so I get that cos x sine x dx is u du. And the integral of u is exponent up by 1 divided by the new exponent. And that would be a half of sine x squared plus c. You may feel like this answer is very different to the other answer. And that's okay. They are less different than you think they are. These two functions are exactly the same, except one is a little higher than the other. So they're going to have the same derivative because at every position they have the same slope because one is just a constant off of the other one. There you go. A trig identity would have done that. Both would be accepted in an exam. You wouldn't have to try and turn it into anything else. You could leave it exactly as it is. If they specifically told you to do it by substitution, then they'd expect a certain answer. Okay, I can also do this one by parts. And I just want to show you how these things work so you can see the strategies that are used. This decision of whether it was substitution was based on me noticing that one bit was the derivative of another bit. And so I could run that through and see what happens. Okay. But I could just as easily do by parts because it's two things multiplied together, and by parts is for that as well. So I could call this u and v, and it would become uv minus uv, the integral of, damn it, getting ahead of myself. Integrate whatever you want. So my decisions are, do I know how to integrate them? I know how to integrate both of these, so that's not going to help. Is one of them going to get simpler? Not particularly. So I just get to choose whichever one I want. So I'm going to do it this way. Yep.
Well, if you do it one way, you're going to get like a lot of minuses.
So the integral of cos would be a plus sign, and so that wouldn't have a minus in it. That's what you're saying? Nice. Minuses are annoying, so good choice. So that the third rule is, will it be less annoying the other way? So here's my rule. U was cos x, u dash was cos x, which means I have to integrate it, and that would be sine x, and v was sine x, and I differentiate, that would be cos x. And I'm going to get u is sine x, v is also sine x, minus u, which is sine x, and v dash is cos x. And I have very helpfully gotten back where I started. But wait. I cover this bit up. I have the integral of cos x sin x dx is equal to this thing minus the integral of, well, sin x cos x is the same as cos x sin x. So I'm just going to write that down just so that it's absolutely clear what's happening here. So that's what I've just figured out. If I add this to both parts of this equation, I'll have two of them here. And so therefore my integral of cos x sin x is a half of sin x squared. Technically, I probably should have put the plus c here. You're supposed to put the plus c in the moment the integral sign disappears. And this wouldn't be the same constant because I would have divided by 2. So I'm going to put d because it's to remind myself it's a different constant. It doesn't really matter because the c covers all possible constants, and in half of all possible constants is still all possible constants. That move of basically going around in circles and trying to achieve the thing that you first started with is a neat trick with integration by parts. Sometimes you have to do the integration by parts twice before you get there. All right. Any questions or thoughts or particular integration problems that were distressing to you that you would like to share at this point?
If you get one like that that repeats itself, is it always going to be able to be done this way?
No.
Yeah,
But
so
most.
the questions in year 12 where you get them and they just keep going until you couldn't do it.
Yep. So, well, they can keep going. You just have to, so there's two parts to that. One is you have to keep a very close eye out to see when it's almost the same as what you had before. Because if this had been a cos 2x sin 2x, then I would have ended up down here with a 4 probably. No, I wouldn't. No, that would have been fine. Yay. Anyway, yeah, if I had a cos 2x sin x, then at this point I would have gotten a sin 2x cos x, and I would have had to do it again. And I would have eventually gotten a cos 2x sin x, but by that time it would have been a 4. And when I move it to the other side, instead of having 2 of them, I'll have 5 of them. And I can divide by 5. So just... it'll have something, and then this would be a half, sorry, no, because I would have integrated it. And then when I do it again, I'll have something minus something plus, now it would be a quarter by this point. And I think it'll be a minus as well. And then what that would mean is when I put this over this side, I'll have 1 1/4 of it. Equals crap here. And I would have to divide by that number.
So you just keep going by parts until you've got essentially the same equation at the start.
Correct, except off by a constant maybe. Or you keep going by parts until you just know how to do the integral and then you just do it. So, yeah. So there are some times when what you'll get at the end exactly cancels out the thing at the beginning and you end up with 0 equals crap. And that's when it doesn't work. And
Does that mean you've made a mistake?
no, it just might mean that the function that you've got just doesn't do that. So if I had had cosh x and shine x, it probably wouldn't have helped that much back here. So, yeah. To do this one, you can make your own trig identity. So make your own trig identity. Cos of, so it's got a cos and a sine multiplied together. The sine addition formula will do that. So if I had sine of 2x plus x, it would have been sine of 2x cos of x plus cos of 2x sine of x. And sine of 2x minus x would have been sine of 2x cos of x minus cos of 2x sine of x. And if I did this minus this, then that would make these bits cancel and I'd left with two of them. So I'll get sine of 3x minus sine of x is equal to 2 lots of cos of 2x sine of x. And I've made my own trig identity. And so now I can replace this with half of this and integrate those. Yeah, so you can if you want, but by parts is probably the go. But if you happen to remember these trig identities, it's a very neat little trick. Yeah, and this is something that is reused in some of the later maths courses, but you can usually just trust that it works. Okay. Right, okay, trig substitution. We're at 12:30. Okay, doing well. Only been going for an hour. Okay. Trig substitution is designed for when you have something that is vaguely similar to what would be under a root sign in a Pythagoras. So if I had a triangle with 1 on one side and x on another side, 1 squared plus x squared would do it. And so trig substitution could work for this, only don't do trig substitution just because it has one of those things in it. So even if this had been like a root, you go, oh, it's got a root squarey thing, trig substitution, go. Don't. The first thing you should do is check if one of the other techniques will work instead. So I could attempt to expand it out. Roots don't expand out, so can't do that. Substitution, I could check if one bit of it is nearly the derivative of another bit. Oh, look, x is nearly the derivative of x squared. It's just off by 2. So this would be a substitution. So I notice that I have an x dx here, which is here. So I'm going to move the 2 out of the way. And then just to make sure I've got this right, that would be root u, which would be u to the power of a half. And so therefore my integral is now the x dx is really a half of du, and this is u to the power of a half. And I know how to do powers. The half multiplied on will still be multiplied on. The u will go, the exponent will go up by 1 to 1.5, which is 3 over 2. And I'll have to divide by that 3 over 2, which is the same as multiplying by 2/3. And so I get 1/3 of u to the 3 over 2, which is 1/3 of x squared plus 1 to the 3 over 2. So the first moral is don't do trig substitution if you don't have to do trig substitution. Try an ordinary substitution, which means checking to see if one bit is the derivative of the thing that you would substitute. All right, so what if that x wasn't there? now I can't use substitution because the derivative of that x squared plus 1 isn't actually there. And if it had just been x plus 1, then I wouldn't have to do any of this because I could just divide by the constant derivative. So I'm still not going to do trig substitution. I'm going to do by parts. I don't know how to integrate this, so it can't be the one that gets integrated. So it's going to have to get differentiated, and this one's going to have to be integrated. So my u dashed is 1, which means that my u is the integral of 1, which is x. My v is root x squared plus 1, which is x squared plus 1 to the half. And v dash would be a half of x squared plus 1 to the minus a half times 2x. Okay, so I've now got u, which is x, v, which is root x squared plus 1, minus u, which is x, and v dashed, which is x on root x squared plus 1. And you're thinking, David, that's ridiculous. That still don't know how to do that. Yes, you do. You ready? If this had been a 1, then this would be arcsine. And that's one of the derivatives you're supposed to just know. Oh no, sorry, crap. Damn it, David. It's not going to work and the world is crap and I hate everything. So, no, not going to work. Sad face. If it had been 1 minus x squared, then that would have been great. And I would have been able to get to where I want to go. So, sad face. Okay. So, yeah. If it had been a 1 minus x squared, then this approach would have worked. What I was going to do is I was going to put a plus 1 here and a minus 1 so that it matches the bottom and I can cancel some stuff out. So, all right, sad face. I am going to do it by trig substitution. Okay. The purpose of trig substitution is to turn this into a thing that is squared. So that the square root will make it go away. Because square roots do not expand out over x squared over plus. But what they do is cancel out squares. So if I can replace this with something that does square, then that'd be great. I'm going to change this to a 16 just to make a point. So I was asked in the chat earlier, how do you decide which trig substitution to do? And there are 2 versions of this, and they are both designed to both do the trig substitution and simultaneously tell you which trig substitution to do. Okay, so one is that the way trig substitution works is that you will use eventually a trig identity to make the square root go away. Or you will use literally Pythagoras theorem because it's the same thing. So I'm going to do both. So the Pythagoras theorem version goes, I'm going to make a right-angled triangle, and I'm going to think which side of the right-angled triangle this would produce. So when I do Pythagoras theorem, the long side is these 2 sides squared added together. So this plus here is going to mean that this is on the long side. And if I put an x and a 4, then that will make this happen. Because then this will be 4 squared plus x squared, which would be x squared plus 16, and the square root would be there. Sweet. So then, if I put my angle here, I'm going to call it u because I'm doing substitution, but you can call it theta if you like. Then this root x squared plus 16 is going to be sec-ish, roughly. We'll get there eventually. But this is the setup. I could possibly put it here as well. But what I want to do is put it in such a way that if I combine the two sides on opposite side of my angle, it doesn't put an x with this. That's what I want to do. So I want the angle here. See this thing? And this doesn't have an x, so I want to put the angle there between them. Well, it doesn't really matter. Do what you want to do. Okay, so what I'm going to have now is that tan of u is x on 4, based on this triangle. And cos of u will be 4 on root x squared plus 16, which means that sec of u will be x squared plus 16 on 4. This is going to replace that. But I'm still going to have to deal with the dx. So from this one, I've got that 4 tan u is what x is. And so if I do dx on du, I'll have 4 of sec u squared is dx on du. And so the dx is now 4 sec u squared du. And this is going to turn to crap. Sorry, don't like it. So this is now 4 sec u, this is now 4 sec squared du, and so this integral is now the integral of 4 sec u times 4 sec u squared du, which is going to require me to integrate 16 sec u cubed, which is not fun in any way at all, ever. I wouldn't recommend it. So I give up at this point. And I hope that the exam says, perform a trig substitution to turn this into an integral involving u, and then stop. Sorry, but do not solve. Sometimes in exams they do that. They say, set this up, but don't solve it. So that's what my hope would be. And I would cut my losses here. It is possible to do this, but now I need to know how to integrate sec cubed, which means I need to do probably partial by parts, because I know how to integrate sec squared. Yeah. So I told you by parts was the plan. Okay, sorry. This is why people get their exams checked by other people before they write them. Yeah. Never trust David to write your exam on the night before. That's not how it's done. Okay, let me do another one that is going to work. No, tell me why this one is not a trig substitution. What's that? So I'm going to repeat that and see if I've got it right. The derivative of 36 pi x squared is negative 2x, which is only a constant off of what this is. So this is an ordinary substitution. So I don't do a trig substitution. Now it's not. This is probably going to be awful, and I'm very sorry if it is. Okay, All right. So I could do my triangle thing if I want again. I've got something squared minus something squared, and doing the minus would be looking for one of the short sides in this diagram here. And so I'm going to put it here. No, the 6 would be there, wouldn't it? Because it's the 6 squared minus the x squared. Cool. And I know that I don't have to actually switch the positions, but I am because I will feel more comfortable. Okay, the reason I've done that is so that if I put my u here, then the x involves sine, because sine of u would now be x divided by 6. And sine is easier to differentiate. Yeah. And so 6 cos u will be dx on du. And so 6 cos u du is what dx is. And now I can replace the entire of dx with this thing. Okay? The whole purpose of this is to get rid of this. So now I'm going to have a look at this. That would be cos of u, would be the adjacent side. And so I've got 6 cos u. Like that. And so now this bit gets replaced with cos u, 6 cos u. This bit gets replaced with 6 cos u du. And then the x squared, that's a whole other thing. I've made it so hard for myself. I'm so sorry. X squared, okay. Well, I know what x is. It's 6 sine u. So x squared must be and now every piece of my integral can be replaced with something. So you'll find when you do trig substitution, there'll be a lot of calculations before you even do the substitution. The x squared was 36 sine u squared. The root 36x. Oh, yay, it is going to work. Yay, I'm so happy. This becomes, where was it? 6 cos u. And the dx became 6 cos u du. So each piece is replaced with the things that you've already written down. And now I get this integral. Trig substitution, as with all substitution, produces an integral you're supposed to know how to do. So I go back to the beginning of my list and I say, do I know how to do the integral of sine u all squared? No. Can I rewrite it? Yes. I'll just try substitution. Nah, I need the sine u. And I just created the sine u from substitution anyway. If I now call it something else, I'm just undoing what I just did. So I reckon I'm going to have to rewrite it. Here we go. There is a trig identity involving sine squared. It would be, well, there's sine squared plus cos squared equals 1, but that would just turn it into a cos squared, and I still don't know what to do with that. There'd be the cos double angle formula. Cos of 2u would be cos u squared minus sine u squared. And so cos it would just as easily be 1 minus 2 lots of sine u squared, because I could replace the cos squared with a 1 minus sine squared. Some people are able to remember this formula off the top of their head. I can't. And now I can rearrange this, and I've got 2 of sine u squared is 1 minus cos 2u. But I don't want 2 of sine u squared. I want 36 of sine u squared. So I'll times it by 18. And that's an integral I can do. Uh, 18 minus 18 cos 2u. And the 18 will become an 18u, because if I differentiated 18u, it would give me just 18. This 18 is times on, it will still be there. The integral of cos is sine, and I'll have to divide by that too. So the integral is done. But I still need to figure out how to put the x's back. All right. I'll go back to my list. I do not have sine 2u on my list, but I do have a sine u, and I do have cos u, and sine 2u has a trig identity. Okay, so u, sine u is x on 6, which means that u must be arc sine of x on 6. And so now I've got arc sine of x on 6. The 9 times 2 is 18. The sine u was x on 6. And the cos u was root 36 minus x squared on 6. And I have now got an answer. I know that's a half because that's 36, and 18 divided by 36 is a half. So, thoughts and questions about what happened here? No. This is how long trig substitution takes. Yes. So here, from there to there. So I went looking back on my first page to find these bits. So there's a sine u here. Sine u is x on 6. So I sub that in. And there's a cos u here. It's this, and so I sub that in. And there was a u, but I'm going to have to free the u from the sine and do arc sine. And that's why I did this trig identity, so that I could find the original sine u and cos u from my original first working at the beginning of this. So in answer to the question, is there an easier way? No. It is probably not impossible to do this by parts with some very creative work, but it would be just as annoying as this. Yeah. Because you can see where the by parts might come from this thing here, but yeah. Yep.
Isn't there like a sex word identity you could use at the start of that?
Here.
Yeah, I forgot what it was, but my friend showed me like a few of these questions using, I think it was like sex squared add 1 equals 10.
Yep. So that sec squared plus, no, just a second, 1 plus tan squared is sec squared. That identity is useful when you've got a 1 plus x squared. So you've brought up a very important point. I could have done this first bit with trig identities instead of a triangle. And I do want to just show that, but the rest of it would be the same. But before I do that, the various pieces of this working were make a decision that you have to do trig substitution. Once you've made that, and not an ordinary substitution or something else, once you've made that decision, you have to decide which substitution to do, which I did with the triangle here, but can be done other ways. And then before you do the substitution, you should figure out what every piece of this is in terms of sine or cos or tan or whatever it is, and replace them all. And then you have an integral that you have to do, and it's a brand new integral. You can imagine that this is the very beginning. And almost always you will have to use a trig identity to do this bit. And then after you've done the integral, you're going to have to look back to your very beginning to sub it in. Okay. Yes, I've only got half an hour, so I'm going to move on to partial fractions, okay? If you want to know more trig substitution, there's more videos on that. Okay? But I will get back to you later on your question about trig identities. Technically, the trig identity I used here was that cos squared plus sine squared is 1, because I replaced this thing which involved a sine with a cos. Yeah. Okay. So I've got a question, will they tell us exponential trig sub or normal trig sub? I don't even know what exponential trig sub is at this point. I presume if they wanted you to use that, they would tell you. There is, oh, Cosh and Shine, right, okay. Cosh and Shine are hyperbolic trig sub, and if they wanted you to do that, I think they would tell you. Yeah. But it is totally possible. It's just you can't use the triangle to do it. You have to use the hyperbolic trig identities. And that's a whole other question, and we can talk about that at another time if you want to know more about that. Okay, the last kind of technique is a fancy way of rewriting things. And it's specifically designed for things that are just a second, rational functions. So a rational function is any function that is a polynomial divided by a polynomial. So polynomial being thing involving 1 and x squared and x cubed and whatever. And the partial fractions process only works for polynomials where the degree on the top is smaller than the degree on the bottom. So just saying, damn it. A rational function is allowed to have a higher degree on the top than it is on the bottom. That's still a rational function, but the partial fractions process only works when the top is lower than the bottom. So partial fraction lower degree on the top, higher degree on the bottom. If you're not already in that situation, you're going to have to do polynomial division to turn it into that situation, or like in one of the assignments this semester, they will tell you a helpful piece of information that means you won't have to do polynomial division. They'll say, oh, I just tell you that the numerator is 1 minus the denominator or something like that, which threw a lot of people off. Okay. So the polynomial division process, I may or may not have time to go through, but it tends to work. I'll deal with that in a minute. The partial fractions process is not really a process per se, it's just a way of knowing how you're allowed to split up a fraction. So the partial fractions process is designed when if you have this in factors with stuff on the top, it should be possible to turn this into separate fractions like that. That's the general idea that I'm thinking in my head. That if this is factorized, then each of those factors produces a fraction afterwards. Okay. You know how I said yesterday that functions are vectors when you do subspaces? This is one of those things. Here we go. Are you ready? I'll do it with an example. Okay. The denominator, if I expanded it out, would have degree 2 there, another 2 there, and one there, degree 5. The numerator is degree 2, which is less, and so the partial fractions is going to work. Don't factorize the numerator, it's not worth your time, and don't expand the denominator, it's not worth your time. The philosophy that this works on, which you don't have to repeat every time you do this problem, but I want to say, philosophy this works on is that I'm going to imagine all the functions that have this as a denominator. That's what I'm imagining. This is what I'm imagining. It's going to take a while. I have to imagine all the rational functions with that on the denominator. Because this is one of them, and in order to solve this problem, I'm going to have to imagine how I would do it for any one of them, for any of them and all of them, so that I can make sure it works for this one. So if I imagine all the rational functions which have that as a denominator, or at least the ones that partial fractions will work for, there'll be, the denominator's got degree 5, so there'll be like something x to the 4 plus something x cubed plus something x squared plus something x plus something. I'm just stressing you do not have to do this to make the process work. You can do it without imagining this, but I just want to give you a reason why. So if I imagine all of these functions, there are 1, 2, 3, 4, 5 unknowns. What I would like to do is instead write them as the sum of some functions instead. I would like to write it as something times a function plus something times a function plus something times a function, and so on. That's what I want to do with partial fractions. There are 5 unknowns here. You have to have 5 unknowns here as well, or you're not going to be able to cover everything. That's the idea behind it. You're gonna, if there's 5 unknowns here for all the possible things that you could have had, then there must be 5 unknowns on this side as well. That's why you need as many fractions as you do. And all in inverted commas, all you need, I reckon I can still get to upper and lower sums. All you need is enough functions that are different that have this denominator. All right, so here we go. This function can be rewritten to have this denominator. if I multiply the top and bottom by the missing piece. And this function can be rewritten to have this denominator. And this function can be rewritten to have this denominator. And this function can be rewritten to have this denominator. And I'm missing one. That's okay. So can this function be rewritten to have this denominator. And they're the rules. If you see a single x or an x minus something, then you need one piece for each of its powers. If you see something with a squared in it that doesn't factorize, you're going to need a piece with a constant and a piece with an x. That's the idea of splitting things up with partial fractions. And then your goal is to attempt to figure out what the correct choices for these numbers are to produce these numbers. So, Hayden's telling me something very useful here. Right, just a second. So I'm just going to reiterate. I have to have 5 terms here because when I think about all of the things that I could have had here, there's 5 coefficients that cover all of the possibilities. And so this process is saying that if I want to make this one work, I'm going to have to make sure they all work. So these have 5 possibilities, which means these have to have 5 as well. So that's why I need 5 terms for this one, because this is a degree 5, and which means the top is degree 4, which means it has 5 coefficients. So just to be really, really over the top, if I had this, it's a degree 1, 2, 3, 4, 5, 6, 7, 8, because it's squared, 9. I'm going to need 9 pieces. So this one, I'm going to produce this piece, and this piece, and this piece. This one, I'm going to produce this piece. This one, I'm going to produce this piece, because it's linear. And this one, I'm going to need 4 pieces for this, because it's got a degree 4. So I would have 1 over x squared plus 1, and an x over x squared plus 1, and I would have a 1 over x squared plus 1 squared, and an x over x squared plus 1 squared. There you go. So if I just have one of these irreducible things, then it will produce 2 things, and if it's squared, I'll get another 2. All right. So the actual problem I had, it's probably going to be quite difficult to figure out. This one would need to be imagined to be the different pieces. They won't ever give you one that is this extremely difficult in your exam. So I'm going to do one that's a bit simpler. I'll do this one. The bottom has degree 3, top is degree 2. And I could separate it like this. something over x, something over x squared plus 9, and something x over x squared plus 9. I mean, I can do it as a times 1 over x. That's the same thing. I'm going to change it just a little because we're going to have to integrate this eventually. I know how to integrate 1 over x. That'll be ln x. That's okay. This would be an arctan eventually if I got rid of the 9. Yep. So it might be useful at this time to get rid of the 9. Now I'll deal with it later. Okay. Just give me a second. If I did have arctan x when I differentiate it would give me 1 over 1 plus x squared. And arctan of ax, no, don't like it. That'd be ax all squared, and then there'd be an a here. Now I'll deal with that later. However, this one I would do with substitution, because the top is nearly the derivative of the bottom. And if it was the derivative of the bottom, it would be a 2 in this spot. It would be a 2x. So I'm going to say it's c times 2x, and that'll be okay. It'll just make things a little easier later. So now I put them over a common denominator, ax squared plus 9. That's the missing piece from the bottom of this one. Yep, no. Yep, same thing. Mm-hmm. Well, because they have the same denominator, I can combine them together. In my head, it's just easier because I know that at the end I'm going to have to separate them anyway in order to integrate them. So I just prefer to start them out separate. And now everything has the same denominator on this side and that side. And so I can equate the tops. All right. And what I'm supposed to do is match up the coefficients. You can also pick values of x and see what equations you get. I'm going to match up the coefficients. So on this side, I've got ax squared, and I've also got a 2c, lots of x squared. And then I've got a 9a, and I've also got a bx. So that's what I've got here. That's a 9, because I expanded this out, and it ended up here and here. So now I can equate the coefficients. So the constant term, 3, which is the constant here, must be equal to 9a over this side, which means that a must be 3 over 9, which is 1/3. The coefficient of x, I've got no x's here and a bx here, and so that must mean that b is 0. And I've got, for the x squared, 1x squared here and an a plus 2c here. But that means that the a, and we know the a is 1/3. And so we've got, oh, whoa, I wrote that wrong entirely. So we've got 2/3 is equal to 2c, which means c is 1/3 as well, which is a coincidence. They don't always work out to be the same number. And so that means that my actual function can be replaced with a on x, so 1/3 times 1 over x, that's this bit, plus b over x squared plus 9, which is 0 anyway, so that's good, plus c, which was 1/3 times 2x over x squared plus 9. Now I have to actually do the integral. And so this will be 1/3 of ln of x. Technically ln of the absolute value of x. And this will be, well, the top is the derivative of the bottom. If I did a substitution, I would get 1 over u. And so I can actually do that because the integral of 2x over x squared plus 9, if u was equal to x squared plus 9, then du on dx would be 2x, du would be 2x dx. And so that integral would be 1 lot of du over u, which is ln of u. So that working is what produces this answer here. So some people include in there just do it thing with its derivative on top. And it goes straight to ln of the denominator. I've never been able to do that, but yeah. Ta-da! Yeah, that's partial fractions. So you may notice that partial fractions, after you've actually done the partial fractions and you're at the point where you do the integral, requires you to know how to do substitution. And so it's not common, it is common in exams for there not to be a substitution question, but to be part of the partial fractions question. But again, in some exams, it's common for them to go, how would you split this up? But don't do it. Yep.
If you hadn't done the thing where you put 2 in front of the c, would that still be valid, just have a different constant?
Yes, if I hadn't put the 2 in front of the c would have come out to be a 1/6, and I would have gotten a 1/6. But when I did this substitution, I would have had a half. Oh, sorry, not a 6. Yes, it would have worked. So everything would have worked out to be the exact same numbers it would have, because the not putting the 2 here would have meant that this 2 would have had to be moved out of the way, and it would have all worked out in the end. I just say this because one of the Mobiuses has this trick. Yeah, and it's nice to have it here somewhere. All right, so they are the techniques of integration that are in Maths 1A. And there's a lot going on. So just one more thing before I do the upper and lower sums. Gonna do that for a second. That's not going to do anything. That's all right. I'm just going to look up something. No, can't find it. Someone sent me a list of problems, but I don't know where they are now. There was a practice exam with all these integrals, and I just thought it would be nice to go through all of them and go, which technique would I use? But I can't find it now. Give me one more moment. You see, I have a lot of people emailing me. Nope, all right. I won't do that then. I would recommend spending time choosing which one to do, and then separately spending time practicing doing the process, because they're both things you have to do. Okay. Upper and lower sums. Okay. when I put this video online, I will put a note to say what time the upper and lower sums bit starts. So if that's the bit you're looking for, if you've got some friends who are wondering, they can find it. Okay. Right. So way back at the beginning when I talked about the fundamental theorem of calculus, I said that it's all about definite integrals. And so upper and lower sums are a definition of what a definite integral is. So given any function, a definite integral is an accumulation of the values of this function across this distance. And when you draw it like this, you can interpret it as an area, but you have to interpret areas below the x-axis as negative in order for the area interpretation to work. But you can just think of it as, you know, accumulating stuff. And some of that stuff is negative, so the negative stuff makes it go down. But this requires us to go, just a second, how do I know what the area is for anything? Like, sure, there's the fundamental theorem of calculus, but it's a bit circular, right, to define integrals as the opposite of derivatives, and then how do you know that that's true if you don't know what an integral is without defining it as a blah, blah, and then what's a derivative? And it all just gets confusing, and there was hundreds of years of mathematicians being confused and trying to figure out how to fill in those details, while simultaneously using calculus because it was useful. So we have to define what it means to have an area. And what mathematicians do is they say, aha, I know. If my function was like that, then I would know the area. Because the area would be this distance times this height. Yes! Integration solved. Not really. But then they went, it's okay. It's okay. If I have a curved function, then I can be sure that if I have the lowest possible height and the highest possible height, then whatever the integral is, it has to be between this area and this area. It's not going to be particularly accurate for this picture. But if I just cut it into a way more slices, then it would be more accurate. And I would be sure that the integral was between some lower number and some higher number. And that's the idea of upper and lower sums. So in a technical sense, you don't have to cut it into evenly sized intervals. You can cut it into whatever width intervals you want, but it's really hard to find formulas for these things if the intervals aren't all the same width. And so we're going to do it with the intervals all the same width. And if it works for them all the same width, then it will work no matter what. All right. So here are the steps. You've got, so this is called the upper sum with one interval. This is called the lower sum, that area, the big area there. This is the lower sum with one interval. And if I had two of them, then this one would be there and then be one there. And then this one would be there and then be one there. And those two rectangles is the upper sum with two intervals. And these two rectangles is the lower sum with two intervals. And you're absolutely certain that the integral is between, the true area is it between these two things. And these two numbers get closer and closer and closer together. And so the actual answer must be whatever number is always between them, no matter how big it is. So here's the steps. First, well, I have a problem, so step 0, but if you're doing this, if you're doing an integral from a to b of f of x dx, the first thing you need to do is cut this interval into n equal pieces. The interval from a to b into n equal pieces, and these are called subintervals. And in this step, you need to know how wide they are, the width of each one. You need to know where the left-hand end of each one is and where the right-hand end of each one is. Okay. So, so when you divide that into pieces, you have to give the person reading it and yourself all of those bits of information. The width of each one is called delta x. And so the diagram is this. Here is A at this end, here is B at this end, and you've cut it into all these pieces. And they are all delta x wide. And that delta x is this distance divided by n, because we had that distance and we cut it into n pieces. The total width divided by n, and the total width would be b minus a. When I'm calculating this, I don't usually actually write down the calculation b minus a. And I'm doing the integral from 1 to 6, the width is 5. The right-hand end of each interval is found by starting at position A and adding on the right number of delta x's. So if I'm here at position A, the end of the first interval is one lot of delta x away from A. So it's 1 plus 1 lot of delta x. The end of the second interval is A plus 2 lots of delta x. The end of the third interval is A plus 3 lots of delta x. So this is A plus I lots of delta x. That's the end of interval number I. The I stands for which interval I'm thinking of. And this is traditionally called xi. It's an x value on the x coordinate that belongs to interval number I. That's why it's called xi. And to get there, we start at position A and we add on the right number of delta x's. And if you want to, you can sub this in there instead of delta x. The left-hand end of interval number I is the same as the right-hand end of the interval before it. So if I want to get to the beginning of interval number 2, to get to the end, I'd go 2 lots of delta I. The beginning would be 1 lot of delta I, sorry, 2 lots of delta x. The beginning would be 1 lot of delta x before that. And so the left-hand end of interval number I is xi minus 1. Because the left-hand end of interval number I is the right-hand end of the previous interval. Okay, sweet. The next step is for every interval, you need to decide where the maximum is and where the minimum is. So first you have to decide where it is, and then you'll sub that value into the function and that will tell you what it is. Okay. So this where are they decision is different in different situations. If you know what n is, like there's only 5 of them, for example, for this function, then you would literally cut it into 5 pieces and you would say, oh, well, the maximum's in the middle of that one, the maximum's at the left-hand end of that one, the maximum's at the left-hand end of that one, the maximum's in the maximum's at the right-hand end of that one, the maximum's at the right-hand end of that one. You would need to figure out what location the maximum is on every interval and then sub it in to figure out what the maximum was. But if you're doing UN, you would like to make the same decision for every interval. You want to look at it and go, ah, it's always at the right-hand side, or it's always at the left-hand side, or it's always in the middle. In this course, when you're given, if you have to figure out as a formula involving n, the maximum will always be at the left, or the maximum will always be at the right. One of those two things will happen. So either it's an increasing function, and the maximum is always at the right-hand end. Or it's a decreasing function, and the maximum is at the left. And if the maximum is at the right, if it's an increasing function, the minimum will be at the left. And if it's a decreasing function, the minimum will be at the right. So your working should say something like, since the function is increasing, the maximum on every interval is at the right-hand end. And the minimum is at the left-hand end. Okay. So if you have decided that the maximum is at the right, then that will mean that the maximum value, the capital MI, stands for the maximum value on interval number I, whatever the actual height or depth of the function is. And this will be f of the position where it is. And if it's at the right-hand end, it will be xi. But if the max is at the left, then capital MI will be f of xi minus 1, because xi minus 1 is what the name of the left-hand end is. And if the minimum is at the left, then little mi, which is the minimum value, will be f of the left-hand end. And if the minimum is at the right, the little mi will be f of the right-hand end. And you should figure out a formula for what that is as accurately as you can. Simplify it as much as you can so that it's easier to do the next stage. And step 3 is to actually figure it out. So you do the capital MI times the delta x. And that's a sum notation. You sub everything in and you calculate. If you know what n is, you don't have to use any sum notation stuff. Literally just figure them out and add them up. If you don't know what n is and you need a formula, you're going to have to use some sum notation formula stuff. One thing I will say is if you have an increasing function or a decreasing function, once you know what one of these is, it's possible to figure out the other one without actually doing the sum notation stuff. Because the little mi's, the minimum on each of interval, if it's going upwards, is going to be the same as the maximum on the previous interval. And so the sums are mostly the same in the middle. Yeah. So you could, if you want to do, just figure out the middle and then add on the appropriate extra bit. All right, I have 20 minutes until the next seminar. I'm going to do an example. Okay, feel free to leave at any time, but students will be arriving for the next one soon as well. Okay. Here we go. Find UN and LN for the integral from 3 to 7 of 5x plus 2 dx. So step 1, divide the interval from 3 to 7 into n equal parts. So the width of each interval is a delta x. Which is the total width, which was 4, divided by n because I've cut it into n parts. The left-hand end, I don't want that. I want to do the right-hand end first because that's easier. Of interval number I is xi, which is 3 plus I lots of delta x, which is 3 plus I lots of 4 on n. And then the left-hand end of interval number I is xi minus 1. Okay. That's that first step done. Nothing else to do. Now I have to decide where the interval is on each, where the maximum and minimum is on each interval. So I'm now going to draw a quick sketch of my function. 5x plus 2, 3 times 5 would be 15 plus 2 is 17. And it's increasing because the slope is 5. That's what my graph looks like. It's an increasing function. I'm going to say let f of x be 5x plus 2 because it wasn't actually stated in the original problem, so I might as well give it a name. And then this is increasing. So the maximum is at the right-hand end of every interval. And the minimum is at the left-hand end. So you need to tell the person reading it how you made the decision of where the maximum and minimum is. So now that I've made the decision, the maximum value on interval number I will be the function value at the right-hand end, and the right-hand end is called xi. And the minimum value will be the function value at xi minus 1. If this is the sort of problem that you get asked to finish, which I don't expect to happen in your exam, but you never know, then you will not, it would be not a good idea to figure out the one with the I minus 1. So sometimes the one with the I minus 1 is the capital M and sometimes it's the little m. Figure out the one with the I, not the I minus 1. So don't always do the maximum first, do whichever has the I. Okay, so this one is 5 lots of xi plus 2, which is 5 lots of 3 plus I times 4 on n plus 2. That's where I am, 17 plus 20 I on n. And now, I'm not going to figure out the little mi, I'm just going to leave it as it is. The upper sum is the sum from I equals 1 to n of capital Mi times delta x. It's always that. We write that first. And I'm going to sub in the bits that I know. the capital MI is, I just figured that out, it was 17 plus 20I on n, and the delta x was 4 on n. And now I need to do the sum. So now I need to use the rules of sum notation. First thing I'll do is note that this doesn't have an I in it and it's multiplied on, so I can bring it out. Some people do that right at the beginning before you even put the delta x in. And with sums, I can do the two pieces with a plus separately. So I can have the sum from I equals 1 to n of 17, and separately, the sum from I equals 1 to n of 20I on n. But then that would have a 20 on n in it that doesn't involve an I, and I can bring that out the front, like that. So I did two things at once there. This sum attached itself to both of those, and then the constant came out the front of this one. And then this is n 17s added together, that would be 17n. And this is 20 on n, and there's a formula for this, it's a half of n times n plus 1. Nearly there. So the n's will divide each other. 20 divided by 2 is 10, and I'll get 10n plus 10. And so I get 4 on n times 27n plus 10. And now 4 lots of 27 would be 112. And the n divided by n times n is nothing, and I'll get 40 on n. It's 112, but 25 times 4 would be 100, and then there's 3 left over times 4, which is 12. Yes, okay. And so that is the upper sum, which means the actual integral will be 112. Oh yeah, there's only 2 of them. Good-o. For some reason, I thought that 27 was 3 more than 25. It's only 2 more. Good-o. Moral of the tale, do not give 4 hours of revision seminar before you do your exam. Okay. And so that's the upper sum, which means the integral is going to be 1 over 108. Because it then gets bigger and bigger and bigger, this bit will go to 0, and this will be the answer at the end. Ready, here we go. Lower sum, we're nearly there. I've got 13 minutes. The lower sum, little m I delta x. I didn't figure out what little mi was, but that's okay, because little mi was f of x I minus 1. Yeah. This is where the magic trick is. So see, if I put I equals 1 into this, then it's really x 0. So when I is equal to 1, I minus 1 is 0. When I is equal to 2, I minus 1 is 1. When I is 3, I minus 1 is 2. So this is the same as this sum. All right, bear with me. So now if I compare this to what un is, un was f of xi times delta x back here. These are almost the same, except this one has I equals 0 and this one doesn't. And this one has I equals n and this one doesn't. And so what I'm going to get is that this is exactly the same answer as starting at 1 and finishing at n, only this one has an extra fx0 delta x, and it doesn't have the fxn delta x. In my head, the picture is this. Here's I equals 0, 1, 2, 3, 4, 5, all the way up to n minus 1 and n. For today, this bit was the upper sum, and this bit was the lower sum. And so the lower sum is the same as the upper sum, but without this and with this, which is what this is about. And so we're very close to the end. That is the upper sum. x0 is the beginning of the interval, which was 3. And xn is the end of the interval, which was 7. And so the un was 108 plus 40 on n. The f of 3, we figured that out earlier in our diagram, that was 17. And the delta x was 4 on n. And then this one was 37. And that's the answer, whatever that works out to be. (17 minus 37, which would be minus 20. Minus 20 lots of 4, so we've got 40 minus 80, so we get 108 minus 40 on n. It is not a coincidence that this is exactly the same as the upper sum, but with a minus instead. That always happens with a linear function. If your function's a straight line, the upper sum will be number plus something, and the lower sum will be same number minus same thing. There you go. So those are those pieces. That last piece is the hardest. Thank you very much. I wish you clear thinking, helpful technology, and calm nerves for your exam.